Okay, so hello and welcome back. So now after we have talked about the mathematical proofs in mathematics and mathematical logic and so on and so forth, what we need to do now, what we need to talk about now is a little bit about rational numbers, irrational numbers, and things like that. And well, these things are I mean, in and of themselves. For example, rational numbers, irrational numbers, and we're going to talk about the fundamental theorem of arithmetic, some theorems about rational numbers and irrational numbers. But of course, sometimes they're not really interesting. Okay, but for example, when you go through a theorem and then when you prove that theorem, sometimes it's not really interesting. But remember that whatever you happen to do as a scientist, as an engineer, as a whatever it is that you do, as a programmer or whatever it is, you're actually using numbers. So it might be that, for example, you read a theorem about, for example, irrational numbers, and the theorem seems to be a little bit boring, okay? But you can actually go inside that proof and see what sort of logic has been used in order to prove that theorem. And then you will actually use that kind of logic on actual numbers, because when you're proving a theorem about irrational numbers, you're actually doing some sort of abstract, or you're not talking about specifically 2 or 3 or so on and so forth. You're talking about, for example, the set of real numbers, or the set of natural numbers, or the set of rational numbers, and so on and so forth. But then what you learn in those proofs, you can then actually use them on actual numbers and do interesting things with them, okay? And moreover, basically, no matter what you happen to do, for example, you do something that you enjoy in electronics, you do something in physics, you do something in other sciences, you do something in, computer science, or whatever it is that you do, at the end of the day, you're actually working with numbers, because everything eventually boils down to numbers and working with numbers. So they're actually very, very, very I enjoy working with numbers. They're very interesting, and it's and the decimal system and the numbers that we have, they're actually, it's a wonderful system, actually. Well, of course, sometimes when you come to theorems, you have to go through the logic is sometimes a little bit I don't know what to call it. It's a little bit not boring, but I'll give you the word if I ever get it. But well, okay. So now let's move on. So now what I want to do here is basically previously, of course you were not there, I was there, but doesn't matter. Previously, we talked a little bit about irrational numbers and some of their properties, and then we talked about the fact that also the real numbers rational numbers and irrational numbers put together made the set of real numbers. And then we also saw a little bit about how to locate basically rational numbers and irrational numbers on a number line, and also we talked a little bit about the fundamental theorem of arithmetic, which seems to be a simple thing, but you can actually use it in many different ways, and it's the foundation of probably almost everything in mathematics. And yeah, and that's basically that. Now what we want to do in here, we want to basically use all of those concepts in order to prove that, for example, square root of 2 is irrational, or square root of 3 is irrational, and so on and so forth. And I know that, well, again, I repeat myself, I know that all of these things are, well, not very interesting, but I need to remind you that you can use all of these boring things in interesting ways once you know how to, once you know your numbers well. Okay, so that's basically that. Okay, so now about rational numbers, irrational numbers, and real numbers. Let's do a quick categorization of these numbers. Let's see what we have. So we started with, from the very beginning, from the top, we started from natural numbers, and we said that basically people made up these numbers, these natural numbers, in order to enumerate things, and in order to simply count things, count objects. So for example, you had 1, 2, 3, 4, and so on and so forth. So the set of natural numbers, which is basically denoted by n, is basically consists the numbers 1, 2, 3, and all the way up to infinity, and that's basically called the set of natural numbers. Okay, so that's the set of natural numbers. Now, once humans got a little bit comfortable with the set of natural numbers, they probably started with philosophy. Okay, and I suppose philosophy started there because when they started with these numbers, they were much more practical. They wanted to count the things that they already had. For example, you have 1 apple, 2 apples, 3 apples, 4 apples, and so on and so forth. But then if you want to count the apples, if you have no apples, and you want to basically express that idea, you need the idea of 0, and I've heard that the number 0 was actually invented by Indians, I suppose. I'm not sure, but most probably it was actually invented by Indians around 6,000 years ago or so, or somewhere around 3,000 to 6,000 years ago or something like that, by Indians. So then basically the concept of 0 was also invented, and then it had, of course, to be added to the set of the numbers that we already had. So then they made up the set of whole numbers, which was denoted by W, and that's equal to basically 0, 1, 2, 3, all the way up to infinity. So, and that was basically the set of whole numbers. Okay. Now, then after that, there was basically this time that people started trading and commerce and all those kinds of things, business and all those kinds of things started probably flourishing between people. And so then people needed to somehow talk about, for example, debts, meaning that, for example, if I have $3 that I can denote with a number 3, a positive 3. But if I owe you $3, that my debt has to be somehow expressed and that way of expression was basically the negative numbers, and then that's basically why how the idea of integers caught on and was invented. And so then the algebraic opposite of these positive whole numbers, of these positive natural numbers, was basically added to the set of whole numbers, and that basically made the set of integers, which is basically let's say 0, for example, or 1, 2, 3, and so on and so forth. That's the set of whole numbers, and the algebraic opposite of these numbers was also added to these numbers. So then you've got -1 and -2 and -3, and so on and so forth. Okay, so then you have the set of integers there, and then I really don't know what happened after that, but in mathematics, I think, and then in mathematics, there was the need for rational numbers. And so there was this set of numbers Q, which is basically the set of rational numbers, and that is basically defined as a number P by Q, such that P and Q belong to the set of integers, meaning that P and Q are both integers, and Q is not equal to 0. So if you have, for example, some number like 3 by 2, that's a rational number, and because this is an integer, and your denominator is not equal to 0, so that's a rational number. Now there are some numbers that cannot be expressed as a ratio of two integers. For example, pi, or square root of 2, or square root of 3, or even square root of 15. Okay, so these numbers cannot be, there is no way to express these numbers in terms of the ratio of two integers, right, like this. And so those numbers have been called irrational numbers, and I think they are denoted, if I'm not wrong, they're denoted by Q prime or Q dash or something like that. So these are irrational numbers. So basically what an irrational number is, an irrational number is a number which is not a rational number. That's an irrational number. That means that if a number can be expressed as a ratio of these two integers in this way, that's called an irrational number. Otherwise, it's an irrational number. It's very simple. Okay, so then basically the set of, you can, we have the set of, basically this whole set of and you can, and then of course you can see that compared, for example, to the set of whole numbers, the set of integers is actually a superset of that set, meaning that the set of integers actually consists the set of whole numbers, or the set of whole numbers actually consists the set of natural numbers, meaning that natural numbers are already in here, or whole numbers are already in here, or integers are already in rational numbers. So then you can, in order to simplify things, you can think of this as all the numbers that we know so far. Is basically we have a set over here, which is Q, which is the set of rational numbers, and then we have another set Q prime or Q dash, and that's the set of irrational numbers. These are two different sets of numbers, Q prime. And then the natural numbers and the whole numbers and integers and all of those numbers are already in a subset of this set. this set becomes the superset of all of those sets. And then if you think of these two numbers together, if you put these two sets of numbers together, when you do that, you will get when you do that, you get the set of real numbers, which is basically denoted by R most of the time with this kind of thing. Most of the time this way. So you have two lines over here and then something like this. So that's the set of real numbers. And then you have also, if you want to make it more complicated, we have also the set of imaginary numbers. There is also imaginary numbers, which is I think denoted by Z. And then if you put these two together, I think you will get the set of complex numbers. I think you get the set of complex numbers. Now I don't really know if this Z comes over here or what, but for now let's just forget about this Z, because I don't know what sort of notation is used here. But I know that there is these imaginary numbers. When you put them together, that becomes complex numbers. And the imaginary numbers are, as you know, these are basically the numbers that contain the number I, which is basically the square root of -1. And then complex numbers basically is some sort of a marriage of the imaginary numbers, and meaning that they're working together, put together. If you put these two numbers together, you get complex numbers. For example, some number like 2 plus, for example, 3i. That's a complex number. And I is basically as an example of an imaginary number, and then that's basically, and 2 is a real number over here. If you put it together with, for example, 3i, you will get 2 plus 3i, which is a complex number. So that's basically these two numbers. Basically, I mean, all of the numbers, as far as I know, all of the numbers that we have in mathematics. Now there is one more thing that of course I'm sure you're familiar with, but we will go over that quickly. And that is how to represent numbers on a number line, which is actually a very important concept. To have basically a graphical representation of these numbers in your mind. You have to know what they actually represent. Otherwise, just some concept in your mind, it's not going to be very practical and helpful. So I'm going to take a few minutes rest, and I'll be back with you. We will talk about the algebraic, the graphical representation or geometric representation of these numbers on a number line. Okay, so about representing these numbers on a number line. So basically, when it comes to the set of natural numbers, of course it's easy. You have fire up my this is 100%. And when you want to represent these numbers on a number line, what you do is that so you have when it comes to natural numbers, you have basically the set of natural numbers. You know that is n is equal to basically 1, 2, 3, and so on and so forth. And so the numbers start at 1. You have to basically represent a point starting from 1, and then, for example, this would be number 2, so that would be 1 unit, and this would be number 3, number 4, 5, and so on and so forth. So that's basically, and usually, of course, there is no point over here, so you have number 1 over here, and then it goes all the way up to infinity. So that's the set of natural numbers. And then when you're dealing with the set of whole numbers, the set of whole numbers starts with a 0. Which is basically W is equal to 0, 1, 2, 3, and so on and so forth. And then you have the number line over here starts with a 0. This is 1 unit, this is 2 units, 3 units, and so on and so forth. And then when it comes to the set of integers, okay. When it comes to the set of integers, what you do is you have your number line over here, and the set of integers is basically I. So you have 0, 1, 2, 3, and so on and so forth, and -1, -2, -3, and all the way up to -infinity. You have to find some point over here, 0, and then this is the positive direction, this is the negative direction, so 1, 2, and 3. This is -1, -2, and -3, and then you go all the way up to positive infinity and negative infinity over here. This is positive infinity, this is negative infinity. Now, once you get to the set of rational numbers, the set of rational numbers would be, as we said, would be P by Q. P and Q are integers, and Q is not equal to 0. So then rational numbers would be some number like for example, 1 by 2. And in order to do that, you have the same number line, 0, 1, 2, 3. Let me do this, for example, 1. This is 2 units, this is 3 units, and this would be, for example, -1, -2, and so on and so forth. And then 1 by 2 would be located halfway between 0 and 1, meaning that you have to divide the distance between 0 and 1 into 2 equal distances, and then that point is going to be 1 by 2. Okay, and that's basically how you do it. For example, if you want to represent the number, for example, 1/8 or -1/8, you have to, since it's a negative number and between 0 and -1, you have to divide the distance between 0 and -1 into 8 equal distances. So this is 1, 2, and 3 over here, something like this, and 1, 2, and 3. So that's 1, 2, 3, 4, 1, 2, 3, 4. And this would be, for example, 0/8. This number over here would be -1/8. This number over here would be -2/8. This number over here would be -3/8, -4/8, and so on and so forth. So then this would be -1/8, for example. And then when it comes to irrational numbers, for example, you're dealing with for example, square root of 2, and there's actually a way to represent, for example, square root of 2, square root of 3, square root of 4, square root of 5, and so on and so forth. And the way that you can do it is using the Pythagorean theorem, meaning that if this is 0, and let's say that this is 1, and this is 2, you know that if you have a triangle with sides 1 unit and 1 unit, so if this is 1 unit and this is 1 unit, then the hypotenuse, the length of the hypotenuse is the square root of 2, because well, you know that if you take this length as A, this length as B, and this length as C, based on the Pythagorean theorem, A squared is equal to B squared plus C squared. So then this length holds, if you know the length of these two sides, then this length A squared is equal to 1 squared plus 1 squared, which is equal to A squared is equal to 2. So A is equal to the square root of 2. So then this length becomes the square root of 2. So what that means is that you take 1 unit over here along this axis and the same distance up here. So this is perpendicular, and the same 1 unit along this line, for example, somewhere over here. Okay, and then the length of this hypotenuse is right now square root of 2. So then you can use, for example, your compass or something like a divider or something in order to measure this distance, and then do an arc basically with this center on this axis, and then that would be, for example, if this is 1.5, that would be, for example, 1.5 would be 1, 2, 3, and 4. So 1, 2, 3, 4, 5. So then this point over here would be 1.4. So approximately you would get an arc somewhere over here. You would get some arc over here, meaning that you put your compass over here and you set the diameter of your compass to this length, and then start by and then you set and then you point you choose this point as a center and do an arc over here with the same radius, and you would get an arc over here, and that would be this arc would represent, basically this point over here would represent, for example, square root of 2. And then of course you can do the same thing with for example, I think square root of 3 would be I suppose there is a way that I don't know, let me see. But you can just keep going in this direction, and you would get something like a circle, a circular triangular thing, and using that you can denote square root of 2, square root of 3, and so on and so forth. But that's not very important here right now. I mean, important thing is that you know basically that these numbers are, what these numbers are actually, one way of representing them is basically this, representing them by the distances that they occupy on the number line. Okay, so that's basically that. Now we want to, what we mainly want to do here in this section, and I have talked so much. I have already talked for 30 minutes, and I have talked so much, and I'm going to talk a little bit more. But the main goal of what we are doing in these few videos is to show that the square root of p is irrational for some p that is prime, that is a prime number. Meaning that, for example, square root of 2 is an irrational number. Square root of 3 is an irrational number. Square root of 5 is an irrational number. Square root of even square root of 6 is an irrational number, although 6 is not a prime number, it's a composite number. But even square root of 6 is an irrational number, because it's equal to square root of 2 times square root of 3, and both of these numbers are irrational numbers. And even if one of these numbers is an irrational number, then still this number would be an irrational number. So that's basically what we want to do here. Now, in order to do that, we need something called the Fundamental Theorem of Arithmetic. The Fundamental Theorem of Arithmetic. And remember that basically the goal of if I could set a goal for all of these for all of the mathematics that I do here, is not from the point of view of examination, or is not from the point of view of any sort of degree or anything, but it's just from the point of view of learning mathematics and appreciating the coherence and the inner beauty and the order there is in mathematics. Otherwise, I don't really care. I mean, I don't really care about any examinations. I don't have to write any examinations, and I'm not working towards any sort of degree or anything. Although having a degree is nice, but for me personally, it's not really required. So I'm not doing all of this to get any of those things. It's just to, first of all, to learn mathematics, and then to be able to appreciate the inner harmony and beauty of mathematics. Otherwise you might actually find all of these lectures boring and time-taking and a waste of your time, probably. I don't know. It depends on you. Okay, so now let's go to the Fundamental Theorem of Arithmetic, see what that is, and then we will get to the rest of the things that we have here. Okay, so now about basically the Fundamental Theorem of Arithmetic. Now, this Fundamental Theorem of Arithmetic is actually a simple idea, very simple idea, and the idea we actually started with. Okay, so the idea of the Fundamental Theorem of Arithmetic, we already know it. I mean, all of us already know this idea. It's a very simple and, well, as the name suggests, also very fundamental idea. And it all starts with, for example, I don't know, probably 6th grade or 6th grade, when you start working with factorization and factorizing numbers and so on and so forth. And for example, you already know that, for example, 2, you can write it as 2 times 1, or 4, you can write it as 2 times 2, or for example, some number like I don't know, for example, 253 is supposed to be equal to 11 times 23, and both of these are prime numbers. These two are prime numbers, and 2 is also a prime number. 1 is actually not a prime number, so I'm not writing 1 over here, so I simply write 2 is equal to 2, or 4 is equal to 2 times 2. Now, so what this, I mean, the idea here is that basically any natural number can be actually written as a product of some prime numbers. And it seems that, I mean, whatever sort of natural number you try over here, you are going to be able to find some prime numbers that if you basically multiply those prime numbers together, you're going to get your natural number. Now, now you can look at this idea as from a different direction as well, or from a different point of view as well. You can also think of this idea as is it possible to get any basic natural number if you get some prime numbers and then multiply them together to get that natural number? Is it possible really? And if you basically, I mean, these are the two, you could think of this as the two different directions, or in the previous videos we talked about the converse of a theorem and the P and Q, and P implies Q and Q implies P. You can think of that, you can think of this as that sort of thing, that if you have a, for example, natural number, you're going to be able to any sort of natural number can be factorized as a bunch of basically prime factors. And also if you have some prime numbers, and if you multiply them together, you're going to get some natural number. So that's basically from two different directions. Now, if you take a collection of prime numbers, for example, let's say you have 2, 3, 7, 11, and for example 23, and if you were allowed to use these, for example, this collection of prime numbers in any way that you wanted, and if you were also allowed to repeat them as many times as you wanted, then you would be getting a large number of natural numbers. For example, you could write 2 times 3 times 7 times 11 times 23, or you could write, and that would be some natural number A, for example, and you could write 2 times 3 times 7, that would be some natural number B. You could write 2 times 2 times 3 times 7 times 7, and then that would be some natural number C, and then you could just keep going, and you see that you would get an infinite number of, not an infinite number, because you have actually an infinite number, because then you would be allowed to repeat these numbers as many times as you wanted. So then then the number of the natural numbers that you got here would actually be infinite. Okay, so so now let's suppose your collection of primes includes, now let's suppose that the collection of the primes that you have here includes all the possible primes there is. So you know that the size of this collection, all the possible primes, of course you have infinitely many prime numbers. The number is actually infinite. So then what that means is that if you have all of that connection at your disposal, then you could actually create an infinite, basically you could create infinitely many natural numbers, right? Okay, so I had to stop here, so I don't know where I took off, where I left off. So basically we came all the way up to the idea that basically I'm going to start from here somewhere. So now let's suppose that your collection of prime includes all the possible primes, meaning that the primes that we have here right now and we did this experiment with. Let's say that this collection contains basically all the possible primes there are, all the possible primes that we have. So in that case, we are going to get all the possible natural numbers there are, if you multiply them together in all the possible different ways. And you know that of course there are infinitely many primes. So if we combine all of these primes in all possible ways, we will get an infinite collection of numbers, all the primes and all the possible basically products of primes, which are composite numbers, which are in turn basically all the natural numbers. Now the question is, can we produce all the composite numbers this way? Now the question is, can we produce all the composite numbers this way? All the composite numbers having the collection of all the prime numbers. Okay, so that's the question that we want to answer. Now, before we can answer this question, let's go and do some prime factorization. So for example, let's say that you have some number over here. I don't really. So for example, let's say that you have the number 64 over here. So yeah, if you have 64, it's 2 times 32, and that's 2 times 16, and that's 2 times 8. And that's 2 times 4, and that's 2 times 2. So you can write 64 as 2 times 2 times 2 times 2 times 2 times 2. And this is basically 6 factors of 2. 2 times 2 times 2 times 2 times 2 times 2, which is equal to 2 raised to the power 6. Okay? So that's basically, for example, one number. Or if you have, for example, let's say, I don't know, 57. 57 is divisible by 3. So 57 divided by 3, you will get 1 times 3, 27. So 9 times 3 is equal to 27. So that's 3 times 19. And 19 is a prime number. So for example, 57 is equal to 3 times 19. Or if you have, let's say, I don't know, let's say you have 124. 124. Then divide by 2, you'll get 62. 120 divided by 2 is 60, so 62, 31, 2 times 31, and I think 31 is a prime number. Let me go over here and see, find my calculators here. Calculator in numbers, open all. So there is basically this website over here that you can use to check whether a number is prime or not. And for example, 31, if you check, it's a proven prime. And I don't really know how we can prove. I do know how you can prove. We will get to that actually. No, I don't really know how you can prove if some number is a prime or not. Hopefully we will see about that. Okay, so so basically then you can write 124 is equal to 2 times 2 times 31, and you can just keep going. That means that any number, if you factorize it, you will get some number of some primes basically, and meaning that any number can be factorized as a product of some primes, or as a product of powers of primes basically. Now this basically what we have been doing so far for such a long time, basically factorizing all of these numbers, leads to some conjecture, that that every composite number, for example 64, 57, 124, can be written as the product of powers of primes. So the conjecture that you can make here, is that every composite number can be written as a product of powers of primes. Of course, this is just conjecture, because no matter how many numbers you try this way, there is no way for you to, I mean, this is basically verification, as we said before in those videos related to mathematical proofs in mathematics and things like that. So this is I mean, what this is verification, and by verification you cannot be sure that you have basically covered all the possible numbers. So then this remains only a conjecture. If you can prove it, then it becomes a theorem. Otherwise it's just, for now, it's just conjecture. Now it turns out that this statement is true. This statement is true. And of course, these statements seem to be simple statements. Okay, you would think that, okay, so I mean, for like, I don't know, from the 6th grade for like 20-30 years, I haven't been doing that actually, but I've been doing that for like 10 years or so. But you would, I mean, a scientist would, I don't know, somebody who has done it for 30 years, for example, would say that, okay, I have always been basically factorizing numbers, and any number I came across, I factorized it as a product of basically some primes. So of course this statement is true. But believe it or not, to prove such seemingly simple statements, you need to know a whole lot of mathematics in order. I mean, a whole lot of mathematics would be required in order to basically prove this kind of thing. Okay, but we don't have to worry about that right now. If you want to become a mathematician later, of course, you can go and read all of that mathematics and learn all required in order to prove this conjecture and prove and state it as a theorem, for example. But well, other people have done it, and as it turns out, this statement is actually true. Okay, and it's actually called the Fundamental Theorem of Arithmetic. It's called the Fundamental Theorem of Arithmetic. And again, the idea is, well, pretty simple, and I have a question over here. Can we produce all the composite numbers having the collection of all the primes? Now, we haven't answered this question yet, okay? The conjecture that we said was true was basically every composite number can be written as a product of powers of primes. But we haven't decided this part yet, and I'll leave it over here. If we happen to do it, good. If we don't happen to do that, then we will have to wait until we happen to do it sometime. But I just wanted to point out the fact that we actually have not answered this question yet. But now, the important thing here is that this idea actually seems to be a very simple idea, but the applications of this idea in mathematics is actually, I mean, it goes all across the mathematics, and actually it turns out to be a pretty powerful idea, and you can use it in many different ways, because it deals with the very threads of mathematics. It deals with numbers. Okay, so and then everything in mathematics finally then basically boils down to numbers. So this has been called the Fundamental Theorem of Arithmetic. And the theorem, if I were to state that formally, is every composite number can be expressed or basically factorized as a product of primes, okay, and this factorization is unique except apart from the order in which the prime factors occur. Apart from the order in which the prime factors occur. Okay, so now the last part over here actually seems to be, I mean, it's a little bit, there is actually no good way to understand this last part, because there is some confusion in there, and I'm sure this has been the best way that they could have that they could actually express this idea, but there is actually no good way to actually understand what is exactly meant by this part. because in the next parts they have actually tried to explain this idea, but then they have managed to do so, but then again they have added a little bit to the confusion again. So but that's basically the best that they have that they could do. Now, this fundamental theorem of arithmetic says that every composite number can be factorized as a product of primes, and it seems that it says more, and it actually does. It says that given any composite number, it can be factorized as a product of prime numbers in a unique way. Any composite number that you might have, it can be factorized as a product of primes in a unique way. So any composite number can be factorized as a product of prime numbers in a unique way. And this is important here. So what it seems they mean by the word unique here is that once you basically list out all the prime factors of a composite number and write it in an ascending order, then that representation is going to be unique to that number, meaning that then there is no other number, meaning that then it's not actually possible to find any other natural number that can have that exact representation, and in that way basically it is unique. Otherwise, if you have, for example, if you have a composite number and the prime factorization of that number becomes, for example, 2, 3, 5, and 7, some number a, for example, the prime factorization of that number becomes 2, 3, 5, and 7. This prime factorization is basically, we take it as the same thing as, for example, 3 times 2 times 7 times 5. This is actually the same thing. Okay, so these are, they are not unique in the way that they have been. They are not unique actually in the way, in the order they have been represented. But if you basically express these numbers in an ascending order, like this, and write it as, for example, a is equal to this exact way, which we have done over here, then this prime factorization is actually unique, and there is no other number. It's not possible that you can find any other natural number that can have this prime factorization. Okay, so, and what that means is that given any composite number, there is one and only one way to write it as a product of primes, as long as we are not particular about the order in which the primes occur. So, and that this is basically the same idea again. So now let's do this. Let's do some notation here as well to basically see what's going on here. Okay. Okay. So basically in general, what we do is that, basically given general is not supposed to be written this way. In general, basically any composite number x, if you have any composite number x, we factorize it as x is equal to basically p1, meaning that the prime number 1, p2, and all the way up to p of n, where basically these factors are primes, where p1, p2, all the way up to p of n are primes and are written in ascending order. Meaning that when I write the prime factorization of x notationally in this notation, what you can, the convention is that you have to write it in an ascending order, meaning that you can then assume that p1 is less than or equal to p2, less than or equal to p3 less than or equal to all the way up to p of n. Okay, so that's basically, that means that these are in ascending order, and we are using basically this equal sign as well. And the reason for that is that because p1 could actually be equal to p2, meaning that you could have, for example, 2 factors of 2 or 3 factors of 2, and so on and so forth. So if you combine the same primes, we will get powers of primes. And then basically once we have decided that the order is ascending, then the way that the number is factorized is basically unique, because then there is no other number that can have the same type of factorization, right? Now that's basically all there is to the fundamental theorem of arithmetic, and that's basically what that is. Very simply is that every composite number, any composite number that you might have, you can express it or factorize it as a product of primes, and this factorization is unique. Okay, so, and unique, of course, apart from the order in which those factors can occur. Otherwise, the factorization is very unique. Now, this is a very simple idea, and everybody probably intuitively understands that. But then it has many different applications in mathematics, in different fields of mathematics, and so on and so forth. And now, in order for you to see how you can actually, in how many different ways this idea can actually be used in proofs and to do different things in mathematics, I'm going to show you a couple of examples, and then we will get to the rest of our work. So I'll see you in the next video. Thank you.